Welcome to PCI's Tech TV mini-series, Getting Started with Python and Geomatica. In this final episode of our mini-series, we are going to create a script that runs a batch orthorectification process on multiple satellite images. The script is going to automatically discover all valid imagery in a folder and run each image through different stages of the workflow until all images are orthorectified. For this slightly more advanced script, we will be introducing some new Python concepts, which include input methods, conditional statements, duck typing, list creation and manipulation, and for looping. We will describe these concepts in more detail as we encounter them when creating our script. If you remember from episode 3, we had one main objective, which was to align the features in our raw RapidEye image to the same features in our accurate control Landsat 8 image. In this project, however, we have two concerns. Firstly, we want our imagery to align well with our control image, but we also want the overlap regions of our input images to align well with one another. So we can see here we have the four input images, the raw images that we're going to process, overlapping the reference source. So what we want to accomplish is we want to be able to make sure that when we go into the image and we compare this image to the reference image, that we have good pixel-to-pixel alignment, or that the features line up. In this case, you can see that they don't. The other thing that we have to be concerned with is that in the overlap regions between the two images, that they line up as well, which you can see that they don't. So these are two things that we have to take into consideration. Now that we have an understanding of our problem, let's begin writing our script. So we're first going to go into our text editor, and I've opened up a file here which basically just creates the template that we're going to be writing into. So we just have comments here that just describe different sections of our code and where we're going to be writing the different blocks. The main resource that we're going to use to help us write this script is the Geomatica Cookbook. So we can go once again just to Google here, and we're just going to type in Geomatica Cookbook into Google, and we're going to go to the first link, which brings us to our Geomatica Python Cookbook. We're then going to look through this cookbook to see if there's a recipe that will help us write this script. So we're going to look in satellite photogrammetry, and we can see that we have one that does a full workflow. It's a satellite photogrammetric batch workflow with user-provided DEM. Since we have a DEM, this is exactly the recipe we're going to want to work with. So I'm just going to click on here, and it's going to bring us to the actual block of code we're going to be using in order to write this script. So let's begin putting this script together. We'll just move these windows side by side so we can use this as a reference. And the first thing we're going to do is we're just going to copy and paste the different modules that are going to be imported into our script. And we're just going to take all the modules from this recipe here. The next step that we need to do is to set up the user inputs. This is where the script's going to prompt the user to get information such as where the input data is and where the output data should be written to, amongst other pieces of information. I'm just going to now manually write the inputs that we need. So we need to know the input directory where our imagery is stored. We need to know the output directory where we want our output orthos to be written to. We need to know where our reference imagery is, and we need to know where our DEM is. We're then going to set these variables equal to what the raw input function in Python returns. So we just type here raw input, and then a simple phrase that we want to be prompted. So we can say input directory path. And we'll just copy this. And we'll change this to output. Change this to reference. And then finally DEM. And we'll just save this step. So now the user is going to be prompted by the programmer, by the code, to input this information, and that in each of these individual pieces of information will be assigned to these variables, which we can then access through our code later on. The next part of the script that we're going to write is the data discovery section. And for this, what we're going to do is we're just going to copy and paste this block of the code. Now that we have that pasted into our Python file here, we're going to have to hack it to modify it so that it works with our particular environment. So the first thing I'm going to do is I'm going to change the input directory that it's going to search through. So I'm just going to change this to input dir so that this will be mapped to here. And this function is basically just going to go through, or this block of code rather, is just going to go through the input directory and find all the valid images that have a particular filter applied to. To figure out what to use for our file filter, we can simply just go to our input imagery, and we can see if there's, so this is the file that we want to load, the .xml file, and we can see if there's any part of this file name that is different than everything else, but is also similar between all the input files. So we can see aux.xml is unique but between the different files, but is the same for all of the XML files. So here we can just simply write aux.xml, and then we have the asterisk in front of it, which is considered a wildcard, so it ignores the information before it, or the string before it. So here we have an empty list, and this is the list that this block of code is going to iterate through or loop through in order to fill this list with all of the different input files, the paths to the different input files. Now that we have this section set up, we can simply go down to the next part of our code, and we're going to copy and paste the part that imports the imagery and collects the GCPs. So we're going to take this entire if or condition statement that also has a nested loop statement within it. I'm just going to copy that into our code. So we'll make our Python text editor full screen to make it a little bit easier to work with. And now we can begin modifying it. So the first thing that we're going to do is we're going to change the ingest link directory here. So this variable. So what we're going to do is we're just going to make it so that we include our output directory. And then we do plus os.sep. And then we can add in just the subfolder that it's going to be writing our ingested imagery to. We also need to add one line here, which just basically is because we're importing ComSat3 imagery, which is, we point to an XML file, so we need to tell it whether we want to ingest the multispectral or the panchromatic. So to do this, we can just go create a new variable. We'll call it raw file underscore ms, make it equal to raw file, and then just going to add a suffix to it, ms. And this part is explained in one of our earlier episodes in this mini-series. So we have a statement here that's going to see if our path exists for our ingest folder. If it doesn't, it's going to create the folder. And then finally we have our call to our function, which is the link function, which is going to basically import the imagery. And this is duck typing. Basically we try the function first and then handle any exceptions later. Whereas in a more common way to do it, or in the past, is that you would try to find all the exceptions first and handle them and then call the function. But we need to do one more thing. We're just going, because we've changed this here, so we just need to add the underscore ms so that this link function is now importing or looking for the files here. This is the string that needs to be passed. So we now have the ingest part of this section completed, so we're going to take a look at the GCP collection section now. We'll change this quickly to our near infrared channel, which we know because we're familiar with the data that it's stored in channel 4. We need to set up our reference image. So if we go back to our folder here, we can go to our reference, hold shift, right click, copy as path, and we'll put that in here. So we'll do the same thing with our digital elevation model. And we're just going to increase our search radius to 250 pixels. And the same thing here, we have a duck typing methodology that's applied when we call the AutoGCP2 function. So now our GCP collection part of the code is set up, so we can move on to the GCP Refinement. So in the GCP Refinement, we're simply just going to change the order. So we're going to make it polynomial order 1. And we're going to change our rejection criteria thresholds to a single pixel. So we want at minimum 1 pixel accuracy. We're going to now add a new variable here. and we're just going to call it GCP seg refin. We'll make it equal to an empty list, and we're just going to add that here. And this is going to return the segment number with the refined GCPs. This is the one that we need for updating our math model. So this part of the code is now set up, and we can move on to the bundle adjustment part of the code. So we can refer back to our Geomatica Cookbook, and we're just going to go into and copy the next segment and work with this. So all the way down to the automatic tie point refinement. So we'll just copy that, we'll bring it in here. We're going to modify our working directory so that it works with the one from above, basically where the user prompts. We're going to just set this to output dir plus os.sep plus bundle adjust. And the same thing is true if it finds that this folder doesn't exist. It will create that folder and all folders in the path necessary for this folder to exist. So we're just going to improve then this part of the code so we can get rid of this line because we already know which GCP segment we want, and that's stored in this information here. So I can just copy this variable, and I'm just going to replace that one with this. So we can see we put it in there. We're going to provide the correct projection that we want to work with. So I know for this data it's UTM-17 and DOO stands for WGS-84. And now we have our bundle adjustment section of the code complete. So we can move on to the last segment or section of our code, which is the orthorectification, or updating the model and orthorectifying the imagery. So we'll go back to our cookbook and we're just going to copy this last block of code. We're going to paste it in here. So here we can hack this so that it works within our code. All we need to do at this point is really just change the ortho directory so that it takes the one from the user prompt. So for this we can just type in output dir plus os.sep, and we'll just define a folder for it, so a subfolder, we'll call it orthos. And these are where our output ortho images will be written to. Same thing is true as this directory will be created if it doesn't exist. Then we can verify that our resolution for output orthos is what we want them to be, which it is, and then we can save this script and run it. To run our script, we can go to the command console, bring it up here. We can just drag and drop our script in there, click enter to begin it. Then it's prompting us to set up an input directory. So we just go to our raw folder that contains our 4 input images, click enter. The output directory path, so it wants to know the output. We're going to provide a new folder for it, we'll call it output. So it'll create that folder here and all the necessary data will be put in there. Then it wants to know the reference imagery, so we can drag and drop our reference image. And finally the digital elevation model. So we'll provide that. So you can see it goes through, it finds the 4 raw input images, and then begins the workflow to orthorectify these images. Now that our process is completed, let's take a look at the results. So I've already loaded the ortho images here on top of our reference image. So if we zoom into an area, for example here, just zoom out a little bit so we can see a few more features. Then by toggling this image on and off, we can see that we have very nice pixel-to-pixel alignment or feature-to-feature alignment between the reference image and this ortho image. Now we can go to an overlap region, for example here, and we can do the same thing, toggle it on and off, and we can see that once again we also have a very nice alignment between the one image here and the adjacent or overlapping region of this image here.